Okay, morning everybody. It's a great honor for me as well to be here. And I'll be talking about the inspiration that Alan has given me. And some of it is really still, some of the things I'll show you still alive and kicking. Right, I'll be mainly talking about the EUV. This is a UV spectrum of the sun taken by the prototype of the SDO Eve satellite. And when I first showed it to Pete Story, he was stunned. He said you could spend a lifetime to understand the spectrum. And it's true. Can you imagine we get one of these every 10 seconds? It's amazing. Now, if you look at the number of photons, you can immediately see, all of you probably know it, that the coronal line, the strongest coronal lines are on this bunch of lines down here. You can see iron 9 here in around 170 angstroms. And the eyes, as Helen showed, observe these regions with great accuracy. And these are the lines that basically, thanks to Alan and Brian, who are both here, were the first to identify these. These are the strongest coronal lines, aside from a couple of magnesium 9 and 10 lines out here. These are the strongest coronal lines in the whole of the UV spectrum, so these are really, really important. So the zeta spectrum and its importance has been talked about by Martin already. And I'm really fond of this paper, this Nature paper, because it was published on the day of my birthday. So it was very inspirational for me. I was only 1 year old, but it was very inspirational. So going back to the Hinode eyes, when I first produced the spectra in 2006, this is a spectrum basically of an active region. What we realized is that about half of the spectral lines were not identified still. And so I had to, thanks to Brian, who rescued a few of the theta pinch plates, the best ones from Rutherford, gave them to me, and I scanned them, and I actually used them. They were really key because their wavelength accuracy and spectral resolution was even better than the Hinode eyes. So they were really key to help me to identify these lines. I'm really happy and proud to have carried on the work that Alan and Brian started. So what I been doing the last 10 years is to do benchmarking. For benchmarking, what I mean is to find the best atomic structure for an ion, then to interact, and that thanks to Helen, as Helen mentioned, with the atomic physicists, Pete Story, Helen, Nigel Barner, we formed this team, to actually calculate the atomic data, finding the right target. That is taking a very long time, as Helen mentioned, 40 years to find the right targets for some ions. And then compare the observed and theoretical wavelengths and intensities for low density and high density plasma. So low densities have been using solar spectra, high density have mainly been using Brian Fawcett's plates. And the results have been a large number of new identifications and revised wavelengths. And this is just a selection of a few of the papers I've done, one paper, or actually more than one paper per ion. Helen has already mentioned the importance of finding the good target and getting the right atomic calculations. This is the A team, the UPUP team. And these are the results, and we published the various results on all these ions. And people with more experience, like Helen and Pete Story, they're saying they're a bit reluctant to say, but I'm feeling quite confident that actually, I think we nailed down some of these coronal ions. I think that's it. We have very good agreement with the observations. But they have more experience. So with larger computers, you can run larger models, so maybe these things will be improved. Now, I just briefly wanted to mention, this is a nice spectrum around these lines that Alan and Brian identified. You see these two blue lines here, they were identified in this paper by Alan Gabriel in 1966. This is the G66. So this is a list of the strongest UV lines, or some of the strongest for iron 11, which was the most difficult ion. And then what I did was I focused a lot on these lines, which are stronger in the eye spectrum because the sensitivity of the spectrum is concentrated around these wavelengths. And I had to modify some of the identifications of these lines. So actually, in 10 years, I only found one mistake in the tables that published by Brian Fawcett, which is amazing. He identified thousands of lines, and together with his collaborators. And so I'm really happy to have continued this work, and actually I managed to identify more than half of the 60 strongest UV lines And again, as I said, the theta-pinch plates have been key to this work. The other thing I would briefly going to mention is these iron 12 lines. You see the strongest line, 195 here, is actually a self-blend, and is used a lot by everybody in solar physics, together with a line which is down here, 188.6, which is also a self-blend, to measure densities. Oops. Yes. I think I was, yeah, these are the density measurements. So you see this is the line, the iron 12, which goes to the ground state, which is a self-blend, and this is the density sensitive line. And if you take the ratio of these two, you get a density map of a solar active region, which is very nice. But as I said, Alan's contribution has been key again, because we identified these two self-blends in a paper we wrote. I wrote together with Helen in 2005, thanks to these plates, to these plates. Now going back to this other issue, Alan has been inspirational as well, because he basically applied the idea that the ratio of lines with different excitation energies, this is an example of measurements from SOHO, Sumer, and the Gracie incidence spectrometer. He measured the electron temperatures in the off-limb corona. So that was inspirational, because I thought, oh wow, this is really good. So can we do something else with some other lines? And I realized that actually the lines observed around 700 angstroms on magnesium 9 are probably some of the best lines. So the ratio of the intercombination line, 706 angstroms, which is this line here, and this line here is temperature sensitive, which is really, really nice. And by the way, these lines will be observed by SPICE, so we are looking forward in the future to actually have very good measurements. These are some measurements I did with the grazing incidence spectrometer, and then I've been doing some work, and I have to apologize here to Klaus, who's here, and Luca, because we were supposed to write a paper. They've done some of the work. I've done the atomic calculations for these ion, and we still have to write the paper. But these are the preliminary results, and they involve the measurements of the temperatures of the limb of the quiet corona in plumes and interplumes. And with the new atomic calculations which I produced, you have an increased temperature. So for example, this is the interlane, these are the interlane measurements. In terms of temperature, you get about 1.5 million degrees. With the new atomic data, it goes up to 2.2. I mentioned this, and now I'm finishing this, basically wishing a happy birthday to Alan, and long life to him and all the spectroscopists which are here. I'm very happy that we are continuing this series of small workshops with spectroscopy. We started with Helen, and then Carol Jordan thought it was a great idea. She wanted to have one, so she organized one in Oxford. And then George Doshek, Tetsuya Watanabe organized one last year. So there is a nice trend in the last few years. Since 2010, we had, this is the fourth of the series, so it would be very nice to continue that. And I finished by saying, if you look at this picture, you can clearly see that Jean-Claude was trying to explain something to Alan, I'm not sure what, and Alan was concentrated to keep his glass of wine steady. So Alan always has his priority right. Thank you.
Thank you very much, Giulio.